difference is 2. No, look, in producer theory, we started with a production function. We define its associated cost function, then found its properties. Now, in consumer theory, we started with a utility function. We defined the indirect utility function and found its properties. It's quasi-convex, non-decreasing properties. But the analogy stops here, because then in production, sorry, in production theory, then we saw an important theorem saying if C satisfies these properties, it is a cost function. But I had nothing like this here. If B satisfies these properties, then it must be the indirect utility function associated to some utility function. Then here we had a bijection between regular production functions, quasi-concave, non-decreasing, upper semi-continuous, and functions satisfying those 5 properties. Here we don't have. No, we do. But I didn't present it to you because it would be too technical. In fact, it was me who found this bijection in the paper you said you were looking at. Okay, so this is possible, but it should be unnecessarily technical in my opinion, although maybe because if you compare my talks with the schedule, you will see that I am very fast, much faster than, so we are already in tomorrow afternoon now, okay? Then I will finish the schedule program maybe 2 days earlier. Then I am considering what to do afterwards. One thing could be to see this, but I'm not sure. I think in view of your interests, in particular your interest, and because you are mathematicians, I am considering to study quasi-convex duality, because you regretted the other day that there is no quasi-convex duality except this duality, which is a kind of quasi-convex duality, no, in my course. So I can easily, and it should be not too technical, and maybe more interesting for you as optimizers. Although you may be disappointed because the theory, quasi-convex duality theory, is not as strong, as powerful as convex duality theory. Well, this is one of the options. I am thinking about several other options. I will decide when time comes. Or maybe from now on I will be slower than I have been so fast. I mean, we will see what happens. Well, there are other analogies. We saw Shepard lemma. In fact, a more general version of it, which says, under suitable assumptions, the demand, the input demand function is well defined, so it's single valued, and is the gradient of C. I'm not writing formal mathematical expression, but just telling you the sketch. Then we are going to see something very similar. So if you want here the input demand, which I'm going to introduce now, not the input, the demand function, it's called, we have no inputs, we have goods. If we want the demand function, we simply just behave to take the gradient of the indirect utility function which in this context is analogous to the cost function in the production theory, and normalize it. Okay? In that case, this was called Shepard's lemma. In this case, what I'm going to prove next, economists call it Roy identity, because they are American. They should say Roy identity, because this Roy or Roy was French. Okay? But economics is the territory of the Americans. Mathematics is much more democratic. You can learn mathematics everywhere in the world. You can come to Varanasi and learn very good mathematics. With economics, I'm not sure. Okay? I work in an economics department. My colleagues, almost all of them are economists. Almost all of them, they studied in the US, and they try to go to the US as often as they can. There are good European universities, maybe also in Asia, I'm not sure. But in Europe, there are some quite good. Mine is also very good. My department is one of the 4 best departments in Spain. There was a time when it was said to be the 5th economic department in Europe, but not at the American level. So I should say Roy, because otherwise the American would get angry. Okay? So let us see Roy's identity. So I'm going to define the demand correspondence. So the primitive here is the utility function. U is given. Our preferences are given and are represented by a utility function. I don't care the properties in principle. Then associated to this U, I consider the so-called demand correspondence defined from the set, now prices are allowed to be 0 in this context, is a set valued matrix from the set of price vectors into itself, but now regarded as the set of consumption bundles. So what is for P in R plus N? X of P is by definition the set of X in Rn, which are affordable under these prices, P. They satisfy the budget constraint. And are optimal under this constraint. So the utility of X is greater than or equal to the utility of Y for every other Y, which is also affordable under these prices. So in other words, is the solution set to the optimization problem. Maximize U of X subject to Px less than or equal to 1. It's a set valued mapping. I'm not assuming anything about you. So it may take empty values, maybe a singleton sometimes, it may be the whole space sometimes. If the price is 0, the demand is everything. Okay, if everything is free, I will buy the whole supermarket. I will not leave anything to everybody else. So if you come after me, you are unlucky. Well, then, but under some assumptions, this may be single valued. So if x is single valued, then we will say that rather than a set valued mapping, we have a function. So this x is called the demand correspondence. Associated with u, or induced by u if you want. In some cases, it can be proved that it is single value. Then we have not a set valued mapping, but a function. No? Is the function such that x of p is the singleton of little x of p. And then we say that we have a demand function. No? It's the same. The meaning of what? Yeah. So you give me your preferences, represented by you, and I introduce this x. This x is a set valued mapping for which the argument are prices. So to a given price vector, what do I assign? The set of consumption goods that you demand under these prices. The set of commodity bundles that you can afford under these prices, and they are the best for you under these prices because you prefer them to any other which is also affordable. Okay? So this is the solution set or the solution mapping of this parametric optimization problem. This is a parametric optimization problem. The parameter is P. So to each value of the parameter, you assign the optimal solution set of the corresponding optimization problem. And this is what we call X of P. So, I mean, I'm using here the economics terminology, but this would be the optimal solution set mapping. Is that the best option that we have for a given price? That when this happens and you are in the supermarket, you don't hesitate what to buy. You have only one optimal solution. You go directly to that shelf where it is located. There is a unique optimal solution. If there is a multiplicity of optimal solutions, you may choose at random among them the one you buy. If there is only one optimal solution, you go for that solution. Okay? If there are many, then, okay, I don't know how will you choose, but you will choose among them. Is this clear now? Well, now, let us see what I mentioned, that this, under some assumptions, this demand can be obtained by just taking the derivative of V, of the indirect utility function. Let us see Roy's identity. This one. So, now we need assumptions. The assumptions are that U is regular, in the sense we saw in this context, means U is quasi-concave, non-decreasing, and upper semi-continuous. We also assume, this is quite acceptable because we saw that these regularity conditions appear in a natural way. Now it comes a very strong assumption, unpleasant in some sense, that the indirect utility function is continuously differentiable at P bar. P bar is strictly positive price vector. So we are interested in finding x of P bar, okay, for this particular P bar. And P bar is in the interior of the price vectors. And also we assume that the gradient of V at P bar, which is assumed to exist, is non-zero. Why is this unpleasant? Because the primitive of this problem is U, not V. So we should give assumptions, ideally we should give assumptions on U, not on V. Okay, if we ask for simplicity to give assumptions on V, then the next step would be to find conditions on U that guarantee differentiability of V. This is a natural question, so it was addressed long ago. Can you guess by whom? I'm talking about quasi-convexity. Jean-Pierre Crouzet. He published a rather deep paper, like almost all his papers, also in the Journal of Mathematical Economics, before I published that one, so maybe at the end of the 80s, with a title something like Duality between direct and indirect utility functions, the differentiable case. And he presents a beautiful, non-trivial theorem saying, if U satisfies this, that, and that, including C1, then V satisfies minus this, minus that, and minus that, because we're moving from quasi-concavity to quasi-convexity. So the properties that he was imposing on U suitably translated to the quasi-convex framework. Then V is also C1. This type of result. Really beautiful and non-trivial at all. Okay? But we are doing only easy things here. So I assume that we are lucky enough to get an indirect utility function which is of class C1 for whatever reason, and that the gradient is non-zero. Which is not a very strong assumption for a quasi-convex function. I mean, imposes something, but not too much. In fact, what we know, because V is non-decreasing, is that this gradient has non-positive components. All the partial derivatives are non-positive, okay? But now here we are saying that at least one of them is strictly negative. Is this clear? Okay. Now, under this condition, what is an element X bar in the demand set corresponding to P bar? And here it comes the crucial observation. Here comes the trick. How we move from maximizing U to V. What is V of P? V of P bar is the optimal value of this problem when P is equal to P bar. And now X bar is an optimal solution to that problem because it is in the corresponding demand set. So this is the crucial, very easy observation that V of P bar is equal to U of X bar. Okay, the optimal value is attained and an optimal solution. I'm not saying anything else. And now, what do you think it would be the role that these regularity assumptions on U are going to play? Where did such assumptions appear? No, we are in consumer theory, forgot production. We produced enough. We are very tired. Now it's time to enjoy and consume. No. We saw that under these assumptions, we can recover U from V. So if you tell me that your utility function satisfies all these regularity properties, then I know you are U. I can deduce you are U from you are V. And the formula we saw is this is infimum of P in R plus plus N such that infimum of V of P such that P is in R plus plus N. No, in R plus N, there is no need to write this because we know that V is defined in R plus N. Such that subject that P X bar, because we have here X bar, is less than or equal to 1. What is the conclusion? What have we done with this simple step? Roughly speaking, to see that maximizing U is somehow equivalent to minimizing V. Because in this minimization problem for V, the optimal solution is P bar. So we have a pair, X bar, P bar. And we have two optimization problems, one involving U, another one involving V. Then X bar is a solution of one problem, if and only if P bar is a solution of the other problem. There is this. And this is the whole idea of the proof. Now, let us apply the KKT theorem, classical with differentiable functions, to this minimization problem. We can, because we are assuming that V is differentiable at this particular point. So let us write the Lagrangian. The variables are P and the Lagrange multiplier, which is lambda, and this is V of P plus lambda Px bar minus 1. So at the optimal solution, which is P bar, we have the gradient of the Lagrangian with respect to P. is equal to 0. The multiplier is non-negative. And the complementarity condition is satisfied. So now, as I used to do in this situation, the first observation is that lambda cannot be 0. Because this would imply that the gradient of V of P would be equal to 0, and we have excluded this possibility. So lambda must be strictly positive. So this factor is equal to 0. Sorry, this is P bar, okay? We are writing this for the optimal solution. So P bar X bar is equal to 1. This means I'm spending all my money, my 1 rupee. Well, and then I copy here the equality gradient of B of P bar plus lambda X bar equals 0, and I multiply this vector equation with P bar, inner product. Then I get P bar gradient of B at P bar plus lambda P bar X bar is equal to 0. But we already know that P bar X bar is equal to 1. So I know the Lagrangian, the Lagrange multipliers. Lambda is equal to minus P Don't get confused by this minus sign. This lambda is positive because this is positive and this is non-positive. So the inner product, by the way, is different from 0 because all the components here are different from 0. They are strictly positive. And here, at least one is different from 0 and all the others have the same sign. Okay? Then we know lambda. So we have almost finished. Then we come to this equation and get that gradient of V of P bar plus lambda. We already know lambda. Times X bar is equal to 1, is equal to 0. And thanks to the fact that this product is different from 0, is strictly negative, as I justified, we can solve this equation for X bar. So X bar is equal to the vector gradient of V of P bar divided by the scalar P bar gradient of V at P bar. and this is Roy's identity. Let us think a little bit about what we have obtained. We started with an arbitrary optimal solution, an arbitrary element in the demand set. And after all this reasoning, we found that there is only one, it must be this one. So here we are having at differentiability points, I mean, locally it's a mapping. It's a single value function. I mean, so if this differentiability holds everywhere on R plus plus n, then on the interior of the domain, then the demand correspondence, economists use correspondence to mean set valued mapping. Okay? So the demand correspondence is single value. So we actually have a demand function rather than a demand correspondent. So what is this saying? That if you are lucky enough to have an indirect utility function which is of class C1 and the gradient does not vanish, then simply take the gradient of the indirect utility function. Well, if you take the gradient, you may be taking too much or too little. You have to take into account the budget constraint. So multiply it with a number such that the cost is equal to 1. So dividing by this scalar makes the effect that if you make the inner product of this with p bar, so you evaluate the cost of buying this vector, then it's equal to 1. Okay? So this is the coefficient which normalizes. So said it in a simple way. The demand element is the normalized gradient of the indirect utility function at that point. But normalized, we mean that we need, this is the normalization. We need P of x bar, P times x bar equal to 1. So we adjust by multiplying with a number that makes this equality whole. And the reciprocal of this number is the appropriate number. Okay? Any question? Now, whenever we obtain a result, either in production theory or in consumer theory, we run to illustrate it with Cobb-Douglas and Leontief. Are you asking for an economic interpretation of this? I'm sure there is, but I don't know. I'm sure there is. If an economist would be here, I'm sure he or she would give you an immediate answer, but I'm not an economist. But you could have made the same question when we saw Shepard lemma. Okay. The first thing I do when I come back to my department is to ask my colleagues, please explain me the economic meaning of this condition. Okay. If you are in touch with economists, that's okay, but I am, yeah, because of course you are in economics department. Yeah. Okay, so I am surrounded by them, but I didn't not learn from them. I am ashamed to say that formally I am a professor of economics, not of mathematics, which sometimes is very troublesome because once I was, maybe 3 years ago, I was invited to give some lectures at a small city 150 kilometers from Barcelona. I had a good friend there, passed away, and then he invited me. And I was in the hotel one morning, and on the front page, there was some news of the type, in our province, I don't know, we have the some economic data. I mean, we have the worst inflation rate, or I don't remember if it was good or bad, but something that was specific to that province. That's okay. But then my friend, I mean, in this small locality, which, so my friend was organizing things very well, etc. He said, this evening will come a journalist for the local newspaper to interview you. Well, okay, then the journalist came with a photographer who took something like 20 photos of me. Only one was published later. And the first question he made is, have you seen the newspaper this morning? What can you tell me about the news about the economic performance in Lleida, which is the name of the place? I said, I had no idea. I mean, I'm not an economist. Do you know how he then gave my response in the new paper? Saying something like, he is me, is so wise that he does not want to commit himself to any interpretation of the result. So he interpreted my ignorance by the opposite, by wiseness. Okay. Then this is a local newspaper you can find in some newspaper stands in Barcelona, and I went to one of them. Nobody buys it in Barcelona because who is interested in that local newspaper? Then I went to that, and since my big photo was on the back cover, big photo, half a page almost, I wanted to have it for me as a souvenir and also for the members of my family, so I bought 6 copies. I'm sure it's the first time that newspaper stand sells 6 copies of that newspaper in Barcelona. Okay. So, Douglas. So, as you already know very well, this is Cobb Douglas. By now you know it better than Cobb and Douglas. And we also computed the indirect utility function, and we saw that it is given by the way, U is regular, okay? Satisfies the regularity conditions required for the validity of Roy's identity. And we computed the indirect utility function, and we found that it is of the type k times the product of pi to the power minus alpha I for some constant k, which depends on A and the alpha i's. But I don't need the precise expression for k now. But look, this is valid only for pi different from 0. So this is true if p1, pn is in r plus plus n. Okay? Otherwise, raising to a negative power is undefined. Okay, then, but look, this is differentiable everywhere on the positive orthant. And all the derivatives are negative because this exponent comes as a factor. So we have the assumptions that guarantee the validity of Roy's identity. Then let's make the computations. So let's compute the partial derivatives to obtain the gradient. So the partial derivative of f with respect to pj at p1, pn is, okay, what's the effect of taking the derivative with respect to pj, that we get minus alpha j, and then the same but with pj with exponent minus alpha I minus 1, which means we get the same expression but divided by pj. This is why I don't need k. So I can write now v of p1 pn. If you allow me, I will write v of p for the sake of brevity, divided by pj. Do you agree? So we know the gradient. So the gradient of p at p is minus v of p, which multiplies the vector minus alpha 1 over p1 minus alpha n over plus. The minus is already there. Okay? Now we need the inner product with p. So we have to make the sum. This is a scalar which comes out. The sum of pi times ai alpha I over pi. And this is exactly what we have always called alpha. The sum of the alpha i's. Okay? Then this means that the demand at P is unique according to Roy's identity and is given by this vector divided, this normalized vector, this vector divided by this number. So V of P disappears. V of P is strictly positive. Okay, because V of P equals 0 as an optimal value is out of consideration because of the strict positivity of the Cobb-Douglas function. Then X of P minus V of P disappears, so we get it's equal to alpha 1 divided by alpha P1, alpha n divided by alpha Pn, which is exactly what we obtained directly by solving the maximization problem. This is not a practical method of obtaining the optimal solution unless we know V. But if nobody has told us what is V, then we have first to compute V. And to compute V, we have first to compute the optimal solution. So if we have V, we have already got the optimal solution. But anyway, this is an important economic relationship. So I'm sure that economists have interpretations of this result, but also they use all these results, they exploit it in a very clever way, making sophisticated reasonings that when this price increases, that happens, and blah, blah, blah. Marginal analysis, what they call. Also, what I was amazed when I got in touch with economists for the first time is to see that whenever you talk to them with some mathematical economics problem, the first thing they do is a drawing. And from that drawing, they try to deduce everything. Sometimes it's misleading because the drawing is just a particular case or something, but they get a lot of intuition from the pictures they get of the result. I will explain you an example of this, which was a little bit amazing to me. Well, now Leontiev, it will be also very short. This is Leontiev. And we found that V of P, the indirect utility function, is 1 divided by PA, A being the vector of AIs, if P is different from 0. Which this has also a very clear interpretation, no? Because A, the vector A, gives you the quantities you need to produce 1 unit of your food. So PA is cost of 1 unit. And you say how many units can I obtain if I have 1 rupee? This is this number. Well, and Leontiev is very nice, concave, not only quasi-concave, non-decreasing, continuous, not only upper semi-continuous, fantastic. And this function on the interior of the domain is differentiable. This makes sense in the denominator as long as P is different from 0 because A is strictly positive and P is non-negative. Okay, so this would be strictly positive. And then it is differentiable. And the gradient is a vector with negative components. Because A has positive components, strictly positive. We just needed it to be different from 0. We have more than that. So Roy's identity holds, which means that the optimal demand under these prices is the gradient divided by the cost of the gradient. Okay, what is P product gradient of VP? If we make this multiplication here in this equality, we get this scalar times PA, which cancels one of the PAs in the denominator. So this is simply minus 1 over PA. Okay? So then if you make this division, then you get minus PA times the gradient of V of P. Again, this is positive because the gradient has negative components. And this is what we obtain directly by solving the consumer utility maximization problem in this case. Because this is a way of saying that the optimal solution under these prices are, okay, we have not finished yet because we have to apply what we know about the gradient. So instead of the gradient, so let's just do things more carefully, okay? So it's minus 1 over PA square A divided by this, so multiplied with, its notation is horrible. I mean, let's first write this in the denominator, so this means minus PA, okay, because 1 over PA would be in the denominator, and times the gradient, which is minus 1 PA square times A. Yeah. So now it's fully correct. So we get the normalized A. So we found directly that the demand for good A is proportional to the amount of good A of the ingredient J that you need to obtain 1 unit of your output, in example. So anyway, this is checking again Leontiev. Our equality by means of Leontiev functions. Some also useful results before moving to the interesting problem of the monotonicity of demand are also related to strict quasi-concavity and semi-strict quasi-concavity. I said that I wouldn't say anything about semi-strict quasi-concavity, but I changed my mind. I will say a few words about it. No? But let's see what happens when under semi-strict quasi-concavity. In all the examples we have seen, the budget constraint is binding. It's active at the optimal solution. Well, we are going to see that this always happens when the objective function, the utility function, is strictly quasi-concave under some other quite natural assumption. So we have the following simple proposition. Suppose the utility function, no, it's semi-strictly. I have to define it. So if U is semi-strictly quasi-concave, and P is a price vector, is such that V of P is less than or equal to the supremum over the whole non-negative order of U of X, then every element in the optimal, in the demand set satisfies the budget constraint with equality. I'm not saying that this is non-empty. I'm saying that every element here satisfies this. If there is no element there, I'm not telling any lie. Okay? Well, but first I have to define semi-strictly quasi-concave. I don't know if we should do it after the break. Okay. So we stop now for 10 minutes.